Okay, we're ready.
Okay, I just want to preface this by saying that this is the second time I've given this, and what inevitably happens when you give the same or similar things multiple times is you forget what you've gone over. Maybe you went over it the time before and you forget to put it in. So I'm going to try my best to get all of the same comments and explanation in, but the later times you really need some help. So please, if there are any questions at all, type them in. Don't feel the need to wait, because I will stop. I don't think this tutorial takes the entire time. We have a cushion at the end, so stopping is not a problem, and it's usually more helpful in the flow than not in the flow. And I'll also say that I guess I want to introduce what's being done. I didn't do as much of an introduction the first time I gave this, but I think it makes what I'm saying easier to understand. The point of this is not to understand the mathematics of solvers or even really every solver that you can possibly imagine. It's not a taxonomy. What I want you to understand is how, I want you to understand how to assess the solver performance and how to do a little better. So this is more like a solver's user manual, like the user manual for a piece of lab equipment. If you've ever been in a lab and you've had something like a lock-in amplifier, let's say, you need to know there's some parameters for operation, like input impedance, and you need to know what kind of signals you can possibly hope to isolate and what kind you can't. But you don't have to understand how the thing was built internally or even the digital electronics that make it work. What you really need to know is how to operate it. So this is sort of an operator's manual for these kind of solvers that we use in Pilot. And that's what I'm hoping to get across. So we're going to start off and talk about controlling the solver. So how do you get the solver you want? And the structure of PETSI, which provides all the solvers for Pilot, is that everything is controlled by options. Now I want to be a little more specific in this too. In PETSI, you don't construct a specific solver. So you don't say, I would like conjugate gradient. You say, make me a linear solver. And then the configuration of that solver is purely dynamic. It's the same for nonlinear solvers. It's the same for time steppers. And this is really a philosophical point we like to make. There is no analytic support for choosing a given solver for any problem almost, because there are many, many equivalent solvers that you could try, and the choice of optimal depends on the physical regime you're in. It depends on the architecture of the machine you're running on that day. And so choosing a solver up front is not only inflexible, but it's really not well-founded based on the math or the practicalities. So I think doing it is a huge error, an enormous error to ever do this in a code. And like PETSI, Pilot is designed to be dynamically configurable this way for those reasons. And thus, any PETSI option can be given to Pilot just by prefacing it with PETSI dot. So I'm going to use two examples to illustrate things. The one we'll be interested in is the hexate example of Pilot. However, everything I do today is directly applicable to, I believe, every other fault example in Pilot. So you could go to TET4, you could go to 2D, and all this stuff would still work. So I just want to make that clear. I'm just choosing hexate because we have to have something definite to run. I'm going to talk at the end a little bit about nonlinear solvers, and I'm not going to use Pilot examples because we haven't had time to really go over them in detail for the nonlinear methods. And you saw how sophisticated they are when Brad gave his presentation about the fault physics. So we're not there yet. So what I'm going to use is better understood problems from Petsy to let you know what the capabilities are. And I think doing more with the nonlinear solvers in Pilot right now I'd characterize as a really research question rather than an engineering question that we think we understand. So let's start. So I'm going to go over a few facts about the kind of solvers that are used in Pilot right now. And hopefully it's not too much. It's the things you need to know in order to think about how they're performing rather than how to build them or what the mathematics are. The kind of solvers we use in Pilot are called Krylov solvers. Now what they do is you take an equation like AX equals B, where A is some linear operator, and you start building a set of vectors. So you might have some initial residual. That's the difference between U and 0 when you're trying to solve this set of equations. In this case, it's the right-hand side minus A times the solution guess. And so you start with this residual, and you keep applying the operators. So you apply it once, that's A times the residual, then A squared, and so on. Now the reason you do this is because this set of vectors can be used to define a smaller problem than your current problem A. This small system can be solved directly with something like Gaussian elimination, and then that small solution provides a guess for the full system. These kind of solvers are called subspace correction because you solve a small problem in a subspace to generate a correction. And Krylov methods are the best known variant of this kind of solver. What should you know? You should know that Krylov solvers are very good at handling coarse details of your system, average stress, sort of variations that happen very slowly over the domain. They're not good at handling high frequency type of behavior, oscillations and such. They are very scalable, which I don't have in this slide, which I guess I should add. That's why they tend to be used. They scale linearly and with time and memory. There's some caveats there, but when the alternative methods, such as Gaussian elimination, the memory goes as the the square, and the time goes as the cube of the number of unknowns. So very rapidly, you can run out of space or time before you get the solution, whereas it tends not to happen with Krylov solvers. However, Krylov solvers, the reason that time is a little weird is they can fail to converge. And so in most situations, you can't use one on its own. You need what's called a preconditioner, which I'll explain in a minute, to help it converge faster. The last thing that the performance issue with Krylov solvers is that they do a lot of inner products. Now, we're going to talk more about that when we talk about parallel performance, because really, you only care about this in parallel. Normally, inner products don't matter at all. In parallel, they become expensive, and so you want to try to minimize the number that you do. So what is a preconditioner? A preconditioner is really just another solver that you use in addition to your Krylov solver to make it more effective. That's really the only viable definition, because there are so many different kinds of preconditioners that are doing different things that are designed in different ways. Preconditioners better be inexpensive, or you're not going to care, and they got to accelerate the convergence. That's the best definition there is. You can see from this equation up here, if we have some preconditioner M, what we tend to do is on every iteration, we apply A here and then also solve some kind of a system with M. So we do a subsolve in every iterate, and that's kind of the idea you have with the preconditioner. But you can think of it as solving a different system where the effective operator is M inverse A, and the effective right-hand side is M inverse B. So there's different ways to think of these things. And I'll talk about examples of preconditioners in a minute. So if we're talking about some kind of user's manual, then the way to begin a problem is always, always, always to take the solver out of the equation. And by that I mean you should never be using an approximate solver if you are messing with your boundary conditions, if you are messing around with the equations or the material model or anything. You should always be using something exact until you've got a solid handle on your physics, on your boundary conditions, on your geometric setup, and kind of what you expect by solving small problems. Once you've gotten through that stage and are ready to look at a bigger problem, then and only then should you be using an approximate solver. And people forget this very often, and when you forget it, what you do is you conflate inaccuracies and other kinds of failures of the solver with inaccuracies in the discretization, inaccuracies in the model, and such. And it makes it very hard to do the kind of science you want to do if that happens. So what we always recommend is to start with something that is guaranteed to work. So you hope. So the LU factorization, or Gaussian elimination, works very, very well in many circumstances. It doesn't do any iteration. It has a very, very small dependence on the character of the problem. And it can also tell you whether you've made a mistake, for instance, whether you developed a problem with a singularity. One of the earliest problems you can encounter is that the LU in PETSI does not work in parallel because it's very hard to do in parallel. Therefore, we use these third-party packages, MUMPS, which is from INRIA, and SuperLU, which is from Berkeley. And so if you want to do LU in parallel, you can, and you just configure PETSI with these other packages. However, it can fail, unfortunately. It fails, as I said, for singular problems, but singular problems tend not to be physically important. However, it can also fail for saddle point problems. The reason is LU needs a non-zero number on the diagonal of the matrix it's applied to, and saddle points have a large number of zeros on the diagonal, so they tend to fail. However, PETSI does contain a replacement solver that can be used with saddles. Now, what is the idea here? Well, as you saw when Brad discussed the formulation of the pilot problem, for just a purely elastic problem, you don't have these kind of saddle points, these zero blocks. And so you can just use LU if you're solving a purely elastic problem or a viscoelastic. However, if you want to include a fault, what our fault model does is introduces constraint. It says, well, we must have this separation between the two sides of the fault, and in order to enforce that separation, we will solve for the traction on the fault surface that makes this true. And when you introduce a constraint in this way, you very often produce a saddle point system. It's a very common formulation with constraints. It's called augmented Lagrangian. And this causes LU to fail. However, we know that for the elastic part of the problem, LU is going to work. So the strategy we want to employ, okay, Miss Maria. The strategy we want to employ is to solve the separate pieces of the problem, which we know how to handle, namely the bulk elastic problem, and then the fault traction problem, which we also know how to handle. It's not too sophisticated. We just need to know, how hard do we have to push these things apart. And then we put these two subproblems together. So this decomposition in PETSI is very general. You have to tell it how you want the problem decomposed.
But Pilot handles this step automatically for you, so you never have to do that. You just know that you can access the purely elastic problem and the pure fault traction problem. And I'm going to show you how that works. And the version of this field split preconditioner that corresponds to LU is the exact full Schur complement solve. So that'll come in a minute when I go over these things. Okay, so let's talk about some engineering details for how solvers report to you in Pilot. Okay, in Pilot, I advise for every run that you give the view option for the solver. In a linear case, you can just view KSP, and in a nonlinear case, you have this SNES view. And what it does is it prints out a complete report of what solver was used. Now, I just want to emphasize how important this is. There is no place in the Pilot code that you can look at that will tell you what solver is being used, because everything is assembled dynamically. This is necessary because you don't want to change the code every time you change machines or every time you change problems or dimensions or anything like that. And so really the solver information is contained in your CFG file, but it may be in a difficult to piece together format because there may be several options interacting. So this report is crucial for us to understand what solver you are using if you ever want some help on making it faster or more scalable or something like that. And I just want to show what the pieces of this are. Now, I hope I can do this pointer thing. So right here, this tells us what kind of solver object we have here. It's a linear solver. That KSP stands for Krylov subspace. And I can't see my thing, so I'm just going to do the best I can. This right here is called the prefix. And what it is basically a name of the solver. Every PETSI object has a name like this. And it doesn't name specific objects, it names chains of objects that belong together. So this linear solver has a name field split 0, which means the first field in the field split, and here it's going to be displacements. In the newest version of Pilot 2.0, this name would be actually field split underscore displacement underscore. And so what this allows you to do is direct options only to this solver. So you could change the type, for instance, from flexible GMRes here to conjugate gradient by directing an option just to that solver. And the same name will be used for the preconditioner associated to this and the matrix associated to it. And so you can control the whole solve. Over here, let's see, it's going to move. It tells you how many processes it's involved in, because in parallel, solvers can be involved with only a subset of the processes, which can sometimes make things more efficient. Now, you can see that all of the configuration options are given, what solver tolerances we use, what kind of preconditioning, and sometimes you'll have a null space attached, which we'll discuss later, and what kind of norm test is being used to decide convergence. The view options will give you, will tell you what kind of solver is being used, but it won't tell you anything about how the solver performed. And for this, we use monitor options, which print out things about how the solver is performing during the solve. So let me show you an example. So if we use this SNES monitor option shown first and run a nonlinear solve, what it shows is the sequence of residual norms. So if you're solving a set of equations f of x equals 0, then the residual is f of x. It's the distance away from 0 that you are. This is not quite the same as the error. The error is the distance between you and your guess for the solution and the exact solution. The residual is basically how well your guess for the solution solves the equations. So here we see that once you get into the domain of convergence for Newton, you double the number of significant digits every time, and this is the definition of quadratic convergence. But all I'm seeing right now are the residual norms at each step of the Newton iteration. I might also want to see, so at each Newton iterate, there's a linear solve, but right now I'm not seeing that. So if I also give the KSP monitor option, I can see the linear portion. And here I show that many, many times linear solves have other linear solves stuck inside. So for instance, we're going to use multigrid, which is an optimal solver for the kinds of problems that that Pilot does. And multigrid has linear solves inside it on coarser versions of the problem. So here there's 2 levels of multigrid that are coarser than the main level, and we're solving these subproblems inside, and we can see all the residual norm performance there. The log summary option is there to give us an idea about the runtime performance of the code. And so where I tend to start is at the top level. So here there's 1 nonlinear solve, SNES solve. Inside that there are 3 linear solves, so probably the 3 iterates of Newton. And there are 12 setups. Now why are there 12 instead of 3? This is a parallel run, and so there were 3 setups, 1 for each iterate, but inside each one there was a setup on each processor for the different subblocks, and so they totaled 12. And you can look at the overall time for the stage. It's not a great gauge of serial performance in the sense that many, many things are going on inside of this, so it's not a great guide to helping you optimize. It is a good guide to telling you what's important. So for instance, this setup phase is 2 orders of magnitude cheaper than the solve phase. So right away I would say, I don't care at all about the setup. I only care about the solve actions. But if we really do want to improve performance, we have to get lower level information. So you can look at these solves and say, okay, I'm interested. Right now what I see is that almost all the time in the nonlinear solve is taken by the linear solve. So forget about nonlinear solves. Let's just look at linear. Setup doesn't matter. And we can say, well, the vector and matrix operations really don't matter. It's the preconditioner application that matters. I believe this problem I was using LU, and so 84% of the total time, but more than 90% of the solve time is taken up by just triangular solves, which don't parallelize very well. So it's not something unexpected. But if you want to know how your machine's performing, you can look at these vector and matrix operations. And so the matrix operation here is getting about 126 megaflops. I think that's pretty good for this processor. It's totally dependent on the memory bandwidth, and there's some elementary calculations you can do. And if you look at the Pilot JGR paper, there's a lot of information about how to do these simple calculations and get an idea if you're utilizing your hardware well. This vec dot product, it's getting a very low megaflop number compared to that. And what this tells us, it should really be compared with the like a vec scale operation or something perfectly parallel. But it's compared with matmul, and it shouldn't be this much less. And what this says is, it looks like there's a pretty slow network here because it's waiting around so that everyone can synchronize and get the same value for the dot product. And so that's kind of one of the reasons dot products are bad in parallel. I believe this was just run in parallel on my laptop, which is why the performance is so poor. You can get these kind of numbers in a more usable form as a Python module by using log summary Python. And that will allow you to do some automated processing, maybe just run some checks to see whether you get baseline scalability, or maybe you want to create charts for a paper or something like that, but it should make it much easier. So that section was about the assessment, really. This is the kinds of information I should be looking at when I'm thinking about my solver. But what are the actions you can take to improve your solver? And that's what I want to talk about in this next section. So basically, everything involves taking a solver that's guaranteed or that we know works and weakening part of it in order to run a little faster, and hoping that it doesn't destroy our convergence behavior or our accuracy. Okay, that's the name of the game. If you're not doing that, then I think you're in a too dangerous regime. You don't just want to code something up and run it and hope for the best. I don't think that's a very good game plan. So, for instance, in the example I showed, we start off with GMRes. GMRes is the thing you should always start off with. It handles non-symmetric systems. It's monotonically convergent. It's stable. So there's a lot of good things. However, it takes a lot of memory. It does a lot of dot products. So you can run faster by using other variants that are not as robust. So for instance, you can try this biconjugate gradient stabilized. It takes less storage. It does fewer dot products. There are a couple of variations of it which are even less robust than that. But so this magenta, every magenta thing in this talk is a link. So here is a link to the table of all of the solvers and preconditioners that Betsy can handle. There are a lot, I think probably close to 100. And there, you know, when you start thinking about how many combinations they can come in, you easily get thousands of tens of thousands of ways to assemble them. So obviously I can't do a taxonomy here or even a summary. What I will tell you is that what you should be doing is looking at some papers, figuring out what the standard has been in the area, what people have done, and the aim of Pilot and underneath it PETSI is to allow you to easily replicate the best examples in your field and then go a little beyond it. So anything that's published, you should be able to replicate from the command line. I would love to see something that we can't, and I haven't so far. And this is the real aim. You should be able to easily reproduce someone else's results and then go a little bit farther, make it a little bit better. The solver is not going to give you a lot of payoff if you're thinking just about optimization. The bigger payoff is going to be in the preconditioner. Of course, that's because the preconditioner is not nearly as well defined, so there's lots and lots of things that can happen. It's a little bit more nebulous. So for instance, I said we could start with Gaussian elimination, or LU. But we can weaken that to an incomplete LU, where you don't do all the work. As you might imagine, this does not converge as well and sometimes fails, but it does have less storage and work, so sometimes it's okay. I don't recommend the ILU preconditioner, but it is a black box preconditioner, so you can always try it. So there's no reason not to try it, but I think it's a horrible alternative in almost every case. There are parallel variants, all of which are worse than the serial variant, so this is just not your friend. I want to talk about things that can actually work. The one that we use in Pilot and that we highly recommend as your first alternative is called Algebraic Multigrid. So let me talk for a minute about multigrid, which you may or may not be familiar with, and try to explain what this is and how it works. Multigrid is a solver that relies upon using information from smaller solves that happen on coarse representations of the problem. Now, you'll recognize this is the same idea as Krylov methods, with the change being how you make the small system that you solve. Krylov methods make it in a very generic, very abstract way. So you're not, the course problem, you have no idea what it might look like. For algebraic multigrid, what you're saying is, well, for multigrid, you'd really like to make just a smaller version of the exact problem that you have. So maybe if you're discretized, if you have data every kilometer in a problem, maybe you go to one where you have it every 10 kilometers and solve that. Naively, that doesn't really buy you a whole lot. But if you're not naive, what you realize is that some solvers are more efficient at extracting what we call high-frequency information. So the wiggles, the local wiggles, and some solvers are more efficient at extracting the kind of what we say low modes, or the information spanning the domain. So if you combine these in the right way, then you can rapidly eliminate the two types of errors, the high-frequency error and the low-frequency error between these grids, while doing most of your solves on the coarser grids, which are much, much less expensive. You can imagine if you just coarse them by factor 2 per dimension, that's in 3D, that's a problem that's almost 10 times smaller. So this is the real payoff of multigrid. Now, the problem is multigrid works incredibly well when it works. The problem is that the setup can be arduous because you need some way to construct small versions of your problem. And as you've seen, the amount of setup and care that goes into every pilot problem with the meshing and boundary conditions and everything, that constructing coarser versions is really hard. And so a while ago, the solver community came up with an automatic way to get smaller versions of the problem that doesn't look at your geometry and doesn't look at your equations. What it does is just looks at the matrix and forms a smaller version of the matrix that's in some sense close to the big matrix. And this is what algebraic multigrid means. It means we're not going to use a geometric representation for coarse. We're going to develop some algebraic rule for making the small problem. Now, the nice part is that it's totally automatic, and the worst part is that it's not quite as robust as the geometric version as you might imagine. But I consider it somewhat amazing that you can just throw a problem in telling the thing no more than the matrix entries, and it can solve it in a scalable way with optimal work. It's just crazy, and it works for unstructured meshes and nonlinear, well, we can talk about the nonlinear variants, but can work in nonlinear problems. It only right now works for elliptic problems, but luckily elasticity is in there in the list of elliptic problems, so it can work. I talked more about this null space issue yesterday. I'm not sure. One thing you should know is that you build up a hierarchy of descriptions of this problem, but when you get to the bottom, things are a little different. At the bottom, you must have a fairly accurate description of the problem at that scale. And geometric multigrid has a little bit of a problem here because it does just have this purely algebraic process, and you tend to leave things out at the bottom. So in order for it to work optimally, you need to tell algebraic multigrid for the very coarsest mesh, what should it be looking for? And these are what we call the near null modes. So for instance, for elasticity, the operator without boundary conditions is invariant to translations and rotations. Now, even with boundary conditions, if you get very coarse, you're almost invariant to translations and rotations, and thus what you want to tell the solver is on the coarsest mesh you better be able to resolve translations and rotations. And thus we feed that information in, and Pilot does this automatically. So you don't normally have to worry about it. However, you can set up crazy problems with other invariants, like two blocks that can slide against each other with no energy or something like that, you could set that up in Pilot in such a way that you would cause the algebraic multigrid to fail, since it would need to know extra information. So if you see the multigrid not converging, you want to think about this issue, and maybe you've done something to the formulation. So there are publicly available versions of algebraic multigrid. This first one, GAMG, that is built into PETSI, so you don't have to do anything. You just provide this option in your CFG file. There are two other implementations that keep us honest. There's this ML from Zendia and this Hyper from Lawrence Livermore. You can download either of those easily during the PETSI configure stage and make them available if you'd like to test this GAMG against them. So if you're solving a purely elastic problem, you throw algebraic multigrid at it, it works really well, and we all go home happy. However, people rarely get to write papers for the purely elastic problem, so we need to do some more. Once you start putting faults in, then, as I said, the way we think about solving them is to split it into separate solves for the separate physics, the bulk elasticity and the fault tractions. And so the good part is that you have a lot of physical insight for those separate systems rather than the fully coupled system, which is really difficult. And we have some optimal preconditioners for those simpler problems, which is good. Then what happens is once you have those subproblems under control, you start asking, well, how do you combine those solutions? The very simplest way is to say, I don't combine them, I just solve them one after the other, which is this Jacobi, is the numerical analyst's way of saying it, or additive, which tends to be what the engineers say. And then this multiplicative, or Gauss-Seidel, is where you solve one, update all of the variables you're solving for, and then solve the next problem. So this is not as parallel, because you can't solve the subproblems all at once. You have to wait for one till you solve the one before it, but it does converge faster. And finally, the most synchronous and most expensive is the sure complement formulation, which roughly you solve one problem, then you incorporate the complete influence of that problem in the next subproblem and solve that. So it's much more expensive, but it converges much faster. So expensive is sort of a weird term here. Each iterate is much more expensive, but the overall convergence can be better because you do a much better job of determining the influence of one physics on another. So I don't want this to be totally abstract. So the first step we're going to take is from words to equations, which makes it more precise. And then after the equations, we're going to take the step from equations to running code, which makes it concrete. So let's do equations first, which is always fun. So I have here the Stokes system, but the really interesting part is that this Stokes system not only describes fluid flow and mantle flow and ice flow, but it's also exactly the system we use in Pilot. In the classic Stokes fluid system, A is the Laplacian. In Pilot, A is the elastic operator. And the linear elastic operator is spectrally equivalent to the Laplacian. So these are very closely related. Then B here is, in the Stokes problem, is a gradient operator, but in the Pilot problem is the operator of rotations which take you into the fault frame. So they are actually pretty different operators. And that's the heart of why our preconditioner for the fault tractions problem is different than the classic Stokes preconditioners for this problem. So I'll talk a little bit about that. So the simplest kind of preconditioner you can imagine, I think, for the Stokes problem is to say, well, what if we just solve for the elastic part, and then we'll just not do anything special for the fault attractions part? And here is how to get that. So,
Matt?
oh, yeah, sure. I just saw your question. That's weird. Okay, so B in the Stokes problem for flow is the gradient operator, whereas in the pilot problem, for us, B is just the rotation angles that take you into the fault frame. And therefore, that's a really different kind of operator from a differential operator to basically an algebraic operator. And that's what makes the preconditioning so different in pilot from, let's say, a Stokes solver like sitcom. And so I'll talk a little, I won't talk much more about that, but you can look in the JGR paper and we go into it a little. So the simplest preconditioner, as I said, is one where you just treat them completely separately. So if you want to get this, you say, okay, do field splitting, but the field split combination type is additive. And I have a mistake on this slide. This underscore, here, I'll show you. This underscore should not be there, unfortunately. So for the elastic problem, I'm just going to say, let's try algebraic multigrid. And for the fault tractions problem, I'm just going to say, don't do anything. This Jacobi says, just use the diagonal of the problem, but since there's a 0 here in the original, it just uses identity. So just what this says is don't do any solving. This has actually been proposed, and it can work, but it's very slow. And it was only used when people didn't know anything else to do. Now, you can slightly improve this by saying, well, let's include the influence of the elastic solve on the fault traction setup. So what you say is, solve the problem with A hat, this approximate solve for the bulk elastic problem. Then this B, then you say, okay, take that solve, then update the values on the fault, which is what B does, right? Remember, it transforms us into the fault frame. And then do whatever you do on the fault, which unfortunately here is nothing. But this does a little better. And this is the multiplicative version, so you can see that we've changed this here to multiplicative. Now, as I said, we were doing a really cruddy job on the fault friction part. So the way to do better is to incorporate more of the influence of the bulk problem on the fault, and this is what the sure complement version does. So here we can give our sure version, which is nice, and the sure version, as I said, can be pretty expensive. So what you can do is say, well, the sure version is an exact factorization of the problem, which I'll show you at the end. So instead of that exact factorization, you can have an approximation. Here we have the diagonal approximation. When you get done working it all out, what that comes to is that you have this nice diagonal operator here, except instead of I, we have this much better approximation to the fault solve called the sure complement S, which for our problem, S is B transpose A inverse B. Now the problem with that is that there's this full bulk elastic solve hiding in the middle of S. And so you have to deal with that somehow. And all of these preconditioners are centered around dealing with that fact. And I'll just note that all of these preconditioners I'm going to show you are discussed and benchmarked in this paper by Dave May and Louis Moresi down here that's from Pepe. It's a very good read if you want to understand what's going on with these preconditioners. It will not explain the pilot preconditioner, which is completely new. For that, you'll have to go to the JGR paper, but it does explain the framework. So here, we are taking account the influence of A on S, but we're still solving the problems completely separately. If we include this, so what we say the factorization type lower here on the bottom, then we solve A, include
include the effect of that solve when we're solving the fault tractions problem. And you can do it the other way, too. I won't talk as much about this. We haven't explored this very much. It didn't really work for our problem. It's pretty specialized to fluids problems. And it really comes down to there's a big, huge difference between the divergence operator and the fault mapping operator. And so this doesn't work. But this does. And this is the full Schur complement factorization of A, B transpose 0. If you multiply these operators together, these block matrices, you will get the original operator. So this is an exact representation. But as you can see, what we do is we have, when we solve this, we solve the upper and lower just have i's on the diagonal. So inverting them is very easy. It's just basically the same as multiplying with them. But the middle operator we have to solve. So the full Schur complement I have to solve with A, I have to solve with S, and then I have some auxiliary A solves laying around, which makes it more expensive than the other ones we saw, but this is exact. And so this is the replacement for LU for saddle point systems. Field split, Schur splitting type, and Schur factorization type full, with exact solves for A and S. So just one slight point, we tend to use flexible GMRes on the outside to start out with. Here's the reason. GMRes is only appropriate for preconditioners that never change. And it might sound trivial, but if your preconditioner involves a subsolve in any way, then it's very easy to change, because if you use a tolerance rather than a fixed number of iterates, or maybe a random start or something like this, you can get some small differences between iterates in your preconditioner, and that can cause your method to fail. So what I would do is always start with flexible GMRes, and then if everything goes okay, you can try backing off, or if you're sure that your operator is linear. But if you start with GMRes, sometimes you get these bizarre errors that are hard to diagnose.